Alright guys, so today we're going to talk about what is a limit. Okay, so a limit is typically something that when we look from the left and from the right, we want to see if it equals the same thing. Alright, so you'll see the notation here. Alright, the limit of f of x as x approaches a number. Okay, and in this case we're using the function f of x equals x squared. So when we plug in 2, we should get 4, right? But the limit, what it does is it gets slowly closer and closer and closer to 2. Okay, so we start with 1.9. If we want to get closer to 2 but not actually be 2, then we'll go to 1.99. We'll just keep extending this out, and this is, each number is closer and closer to 2, and you'll see that when you plug in, you'll get 3.6, 3.96, 3.996. See how it's like basically 4, but not actually 4. If we rounded, we would get to 4, but it's not quite there yet. So that's considered the left-hand limit, because this is, if we look at a number line, okay, we've got 1, 2, 3. I'm emphasizing the 2 because that's where our limit's approaching. We're getting closer and closer to 2 from this side. That's from the left side. Now if we look at the right side, we'll look at numbers that are greater than 2, so we'll start at 2.1 and then 2.01, and we'll just keep increasing the zeros, the place value, so that we're getting closer and closer to 2, and you'll see that as we plug it in, we get closer and closer to 4. So this is considered your right-hand limit, okay? So 2 from the left is considered 2 minus, because it's slightly less than 2. 2 from the right is considered 2 positive, or 2 plus, because it's slightly bigger than 2. So what we need to do to make sure that a limit exists is that the left side equals the right side. Alright, that's when we know that the limit exists. So we're going to look at a couple examples. Alright, so if we find the limit as x approaches 2, the simple approach is to just plug it in. Okay, we know that the function's continuous, and same for here. The answer is just 27. You're just going to take whatever this value is right here, the 5, and plug it in for the function. Okay? There are some simple algebraic rules that you'll need to know. Okay, so the first one is, let's say we've got a function and we're going to multiply it by a constant. K is a constant, which means it is a number. Okay? When we're doing that, we can just take that constant and move it out front, kind of like we're undistributing something. Alright, if we distribute it in, then it moves inside. So an example of that is, let's say we've got 3x squared. Well, we can kind of ignore that 3 because it's a constant and it's just multiplying. So then we can take the limit of x squared as x approaches 5 to get x squared, we know, is 5 times 5, so that's 25. Then we can multiply it by 3 and we get 75 back. Okay? Another rule is, let's say we've got a binomial, which means there's 2 terms, or a polynomial, which means there's 2 or more terms. Then what we can do is split them up into different functions. So if it's still x approaches a certain letter or number, then we can just break it up. So say we've got f of x plus g of x. Well, we can. So let's say we have the limit as x approaches 5, x squared plus x cubed. Well, we can kind of distribute the limit to both because they're both terms. So the limit as x approaches 5 of x squared we know is 25. Limit as x approaches 5 of x cubed, okay, well that's 25 times 5, so 125. And then we add those up to get 150. Just like we can do that with addition, we can do that with multiplication, okay? So our example here is we've got 2 functions, all right? We can distribute this to the first one right here and distribute it here to the second one. So the limit as x approaches 5 of x squared plus 1, okay, that's 25 plus 1, so this part's 26. Notice that it is still multiplying in between, so we need to keep the operation that's still there. And the square root of 5 minus 1, which is 4. Square root of 4 is 2. Oop. Try that again. 26 times 2 is 52. Alright, so here's when it gets tricky. When we're finding the limit as x approaches 0, if there's no denominator, you're fine. Plug it in, move on. You should end up with 0 at this because every term has a variable, and every variable will turn to 0. The tricky part is when you start to have 0 on the denominator. Okay, if you plug in super small values of x, we're going to do 0 from the left and 0 from the right. 0 from the left would be like negative 0.1. Okay, that's close to 0, but not quite. 0 from the right would be positive 0.1. And we'll get closer and closer and closer to 0, okay? As we do that, you'll see that the closer to 0 you get, the higher the y value is. So this is actually going to approach infinity for the y value. Now, since they both, the left and the right, they both approach infinity, the limit is equal to infinity. Where you get into trouble is equations like this, where if we plug in 0 from the left, okay, let's actually clarify this. When you plug in a negative here, you square it, it turns to positive. So that's why it goes to positive infinity, and a positive divided by a positive is still positive. So that's why they both go to positive. Whereas down here, my variable on the denominator isn't squared. So if I plug in values from the left, it's going to go down, 0 from the left. Whereas I plug in values from the right, it's going to go up. So that's 0 from the right. So what we end up with is a graph that looks like this. Okay, now, as x approaches 0, which is our y-axis, the left is going down, the right is going up. Therefore, the limit, what we call d and e, does not exist. Okay, you can't have one going to negative infinity and the other going to infinity and say a limit exists. So, what if we plug in as x approaches infinity? Okay, well, as x gets bigger and bigger, the value of the function actually gets smaller and smaller. So instead of it going to infinity, the bigger the number it is, it's going to be 0. So like, let's say we plugged in 1 over 100. Okay, that's going to be 0.01. But if we plugged in 1 over 1,000, 0.001, right? It's going to get closer and closer to 0 the bigger the denominator is. So as x approaches infinity of this function, it's going to get closer to 0. If you're ever confused, try plugging in numbers and then get closer to the actual number. Here, if we plug in negative infinity, it doesn't matter that it's negative, it's still getting closer to 0. So since, just kidding, yeah, it still gets closer to 0, okay? So there's, sometimes we call it the positive 0 and the negative 0. It doesn't matter because it's still super close to 0, right? If 0 is our number line, as we're approaching it this way and approaching it this way, still getting closer to 0. Alright, now here's where it gets a little complicated. Let's say we've got two constants for a number up top and a exponent. Okay. Anytime we have a constant up top and a variable on the bottom, as long as the variable that the exponent is positive, then the limit will always go to 0, whether it's approaching positive infinity or negative infinity. Okay? But what happens if we don't have a constant up top? Okay? So, this actually gives you a little bit of text, so I'm just going to read it. When you have variables in both the top and bottom, you can't just plug in infinity into the expression. You'll get infinity over infinity. So, we're going to do a technique, okay? We're going to take the smallest exponent that we see anywhere in the function, okay? It could be on the top, it could be on the bottom. And we're going to divide every single term by it. So, the smallest variable, smallest exponent is an x to the 1. So, I'm going to take and divide that into everything. What that does is my x's cancel out here and here, so I'm left with 3 plus 5 over x all over 7 minus 2 over x. And the reason this works is because when you plug in infinity, this goes to 0, this goes to 0, and we're left with 3 over 7, and we now have an answer to the problem. Here, our largest, I take it back. We want to divide by the smallest. No, we want to divide by the largest, guys. I'm sorry. Divide by largest exponent. And what I mean by that is the variable with the largest exponent. Variable. Divide by the variable with the largest exponent. So our largest exponent here is x squared, so we're going to divide each term by x squared. The reason we want to do that is so that we can get every term that has a variable with an exponent smaller will go to 0, so those go to 0 and those go to 0. That way I'm left with 8 over 16, which I can reduce to 1/2. So here's what looks like a pretty complicated one. My largest exponent is a 10 for the variable, so I'm going to divide everything by an exponent, or I'm sorry, divide everything by x to the 10th. Okay. So we're left with these go to 0 and these go to 0. Negative 3 over 33 I can reduce to get negative 11. Negative 1 over 11. Okay. Now, let's say we have an exponent that if we divide by the biggest one, we're still left with an exponent on top. So like if we divide this, we would get divided by x to the 7th. It would cancel out to 0 on the bottom. Okay. So if the highest power of an x in a rational expression is in the numerator, so our highest power is x to the 7th, and that is only here, then regardless of whatever we do, it's going to approach infinity because that numerator is now bigger than the denominator. And the bigger number it gets, the more it's just going to go towards infinity. However, let's say the highest power is in the denominator. Then instead of getting bigger and bigger and bigger, the denominator will continue to get bigger, but the numerator won't. So it's going to approach 0. So here's an example of that. Okay, so if we just flip these, our highest exponent is a 7. Okay, that's going to make both of these go to 0, right? And we're just left with 0. And I don't know if you saw the pattern in the last couple ones, but if the highest power of an exponent is the same, so we have x to the 7th, that's our highest, then do you see how the 5 and the 16th, those are the coefficients of our highest exponents? That is also our answer. That's going to be the same pattern for every time. So when they're equal, they are the same. So let's just go back over that really quick. So we've got when the numerator is higher, it goes to infinity. Okay, think bigger up top, bigger number. When the denominator is higher, then you've got a bigger number on the bottom, so it's going to go to 0. So we've got a small number up top and a really big number down here. It's going to approach 0. And if they're the same, then the coefficients stay the same, and that's our answer. Okay, we're almost done. Now we just have to talk about the limits of trig functions. Okay, so you will have to see what happens when the trig functions go to 0, okay? Now, this is something that I want you to just memorize. Maybe you want to write it on a flashcard. But the limit as x approaches 0 of sine of x over x is 1. Okay, it's a rule. It's kind of like been accepted. It's been proven over many years. Okay, it might seem really strange, okay, but right here in the text it says if you look at the graphs of sine of x and x, they approximately have this same slope near the origin, okay? And because x and the sine of x are the same as x approaches 0, their quotients will be very close to 1. So in that case, in addition to having this rule here, this one, right, if we plug this in, doesn't matter what we get, we're going to get 0. Okay, the limit as x approaches 0 of tangent x is also going to be 0. Okay, so here is our second rule. So sine, we just had sine x over x. For cosine, we actually have to minus 1 because cosine of 0 is 1. So we have to take it away. So how do we use those to apply them to math or to the calculus that we've been learning today? Let's say we've got this example, okay? We're going to rewrite that as 3 times the sine of a over a, and we're going to say that a is instead x, okay? So we used what's called substitution, right? We had 3x and x, all right? So we're going to substitute a letter for 3x. For example, in this case, it's going to be a, all right? So when we plug it in, we can now move that 3 up front. That's a rule we learned earlier. And sine of a over a is 1. So 3 times 1 is now 3, okay? And the way that we did this, it's a simple little trick, right? We multiplied both top and bottom by 3, which could reduce, but then that allows us to say that this is a as well as the denominator is a. So how do we do that when we've got a more complex problem? We've got sine of 5x over sine of 4x. So we're going to have to get a little bit more sophisticated, okay? So first we're going to make sure that both of them are over x, and the way this works is because we're dividing both top and bottom by x, we're technically still keeping the value the same. And then we're going to do the exact same thing that we did. We're going to multiply the top and bottom by 5, the top by 5 and the bottom by 4, okay? So what that does is it leaves us with those coefficients 5 over 4, because sine of 5x over 5x, that goes to 1. This goes to 1, and we're just left with 5 over 4. Okay, we have 2 more rules. 3 and 4. So let's say we have a number here, and we don't have it here, okay? If we multiply, like in the very first example we did with trig, we had 3x and x, right? Well, notice that the answer ended up being 3. It was just the coefficient here. Whereas if you have sine of a and b, we can do the longer method, or we can just remember that when it's sine and sine, whatever the coefficients are of the x terms, that's going to be our answer for the limit when x approaches 0. All right. We only have a couple more examples, and then there's some practice problems if you want to try. So let's look at this pretty complicated example. We have the limit as x approaches 0, x squared over 1 minus cosine squared. Now, we're going to use our trig identities to replace this denominator with sine squared, because if you remember correctly, sine squared x plus cosine squared x equals 1. Alright, so then this becomes sine squared x. Alright, if we expand it, we can say that this is x over sine x and x over sine x. Both of those equal 1, so therefore the whole thing equals 1. Okay? So here's a couple of problems that you can try. The answers are there. Alright, so if you want to pause it and try it before you actually check your answers. Okay. And then here's a couple more problems that you might want to try. So find the limit of x plus 2 all over x minus 3 quantity squared as the limit as x approaches 3. try number 4. And here's 5 and 6. So at any point, just pause the video if I'm going too fast, because I know I went way too fast. But pause it, go back over it, listen to it, come back in with questions if you have any. All right. There's also a practice set of problems that you can do. All right. So feel free to try these as well. I have the answers in the textbook, so you guys can just come in and check your answers. All right. But I'm just going to give you these 6 for the regular ones, and then I'll move it over and let you try 6 of the trig ones. So here are more trig. All right. The next video will be on continuity.